Welcome, everybody, and thanks for joining us today in person and those watching on streaming. Our speaker today is a pioneering researcher whose work includes development frameworks, programming languages, operating systems, and storage systems. He's the creator of the TCL or Tickle programming language and is well known for his work on Sprite network operating system and log structure file systems. He has 14 years of experience in the industry where he founded two companies, Scriptix and ElectricCloud, preceded by 14 years of experience as professor of computer science at University of California, Berkeley. He's currently a professor of research at Stanford University. He's a member of the National Academy of Engineering and has received numerous awards, including ACM Software System Award, ACM Grace Murray Hopper Award, National Science Foundation Presidential Young Investigator Award, and the UC Berkeley Distinguished Teaching Award. Large-scale web applications and changes in the DRAM technology are dramatically altering the landscape today. Our speaker is again pioneering new storage systems to take advantages of these trends by building RAMCloud, which is the topic of today's talk. So please join me in extending a very warm welcome to Professor John Ousterhout.
Thank you. Today I'd like to talk to you about a research project that's going on at Stanford in the area of high-speed storage systems for future data centers. So for a little bit of background, people have been using DRAM in storage systems essentially forever. So I can certainly remember it back to the earliest days of the Unix operating system. Usage has gradually grown over the years, and over the last 5 or 10 years, we're seeing dramatic changes in the way people use DRAM. The DRAM is becoming the main storage system for many applications rather than just, say, a cache in front of a larger storage system. So for example, in 2009, Facebook had about 200 terabytes of data total in their structured data set, ignoring images. And they had about 150 terabytes of memory in caches throughout the system. So they had enough memory to store 3/4 of all the data in their database. And of course, there's systems like Memcached that make it very easy to use memory for storing large amounts of information. And the large web indexes have been keeping everything in DRAM for ages, since the early 2000s. So DRAM in storage systems is not a new idea, but it's becoming fundamentally more and more pervasive. But if you think about the way DRAM is used today, there are two problems with that. The first is that it's pretty clumsy as a developer to try and use large amounts of DRAM in your application. For example, you typically end up having to have some other secondary storage to get durability out of the system. And so you end up with a lot of extra code in your application to manage the relationship between the backing store and the information in DRAM. The second problem is that you only get a very small fraction of the potential performance out of DRAM in most applications today because, for one example, DRAM is typically organized as a cache, and cache misses are extremely expensive. And then second, you still have to manage the backing store, which often means things like synchronous writes in order to have safe storage, and that ends up eating up a lot of the performance of DRAM. So the goal for RAMCloud is to build a general purpose storage system that's based in DRAM that makes it really easy for developers to take advantage of the full performance potential of DRAM. That's the goal. So maximum performance and really easy to use. The basic ideas behind the system are that first, most important, every byte of data lives its entire life in DRAM. There is no such thing as a cache miss in RAMCloud. So from birth to death, all data, always in DRAM. Second thing, which I'll talk a little bit more about later on in the talk, is that even though the data is stored in DRAM, which of course is volatile, we have techniques in the system to ensure the same durability and availability you might get with a disk-based system otherwise. So you can trust the data to last over long periods of time and to be both durable and available. And I'll show you how we do that. And furthermore, we do that in a way that is essentially free and has no impact on the performance of the system. So we get DRAM performance and disk durability. There are two things about the system that I think are interesting, both from a research standpoint and also in terms of its potential impact. The first of these is that we've designed it for large scale, so thousands of servers. We're trying very hard not to make any design decisions that would keep us from getting to at least 10,000 servers in the system. We haven't actually tried to get there yet, so we've probably blown it in some respect we don't know about. But our design goal is to have thousands of servers, hundreds of terabytes of storage in the system today, and in the future, significantly more than that, potentially petabytes of storage, all in DRAM. So scale is the first thing. The second overall thing that makes the system interesting is to push for very, very low latency. And this is, of course, all about achieving the performance potential of DRAM. So our goal, actually we've already achieved this at small scale, is to provide 5 to 10 microsecond access to the data. That is, get to any byte of data in the system from anywhere in your data center in 5 to 10 microseconds. So if we can do all these things and make it work, I think the most interesting potential impact is that this could enable a new class of applications that couldn't exist today. Applications that run at very large scale and manipulate very large data sets very intensively. I'll try and give you some examples of what those applications might be as we go through the talk. And by the way, I'm happy to take questions along the way. Don't feel like you need to wait to the end. OK, so that's the introduction. Now let me do a once-over very lightly about RAMCloud. So RAMCloud is designed for data centers. And as you all probably know, in today's data centers, particularly for large-scale web applications, the machines in the data centers tend to divide up into two groups. There's the application servers that run web front ends, and there's a bunch of storage servers that manage data in the back end. The idea for RAMCloud is to take a whole bunch of what used to be disk-based storage servers, on the order of thousands of them, put as much DRAM as you can afford to put on each machine. And today, that's about in the 32 to 64 gigabyte range. If you put more than that on a machine, they start getting so expensive that you're better off just buying more machines. But I think that number is about to jump up to 256 gigabytes or maybe even more. So put as much DRAM as you can on each machine, and then build a software system, which is RAMCloud, that aggregates all of these servers together to provide one coherent storage system that looks like a single storage system for the entire data center. As I mentioned on the last slide, again, the two key attributes, all data and DRAM, and we want to figure out how to make this durable and available so application developers don't have to worry about managing a separate backing store. So if we can do this, we think we can attain a pretty interesting level of performance. The first one is throughput. We believe an individual server should be able to sustain on the order of 1 million operations per second, small reads or writes. So if you aggregate that across, say, 1,000 servers, then you can do an operation for every human on the planet every 5 to 10 seconds. And the second thing, as I mentioned on the last slide, is low latency access. And what I mean by that is starting from an application server in a program running at user space to get across a data center network with on the order of 100,000 machines in it to a storage server, any of these storage servers, into the RAMCloud servers and back with a small amount of data, 100 to 1,000 bytes of data, do all of that in 5 to 10 microseconds. Now you may think I'm crazy for that, and actually with today's networks you can't do that, but we think that with the networks that are going to be available in a few years that will be possible. So what would a configuration look like today? Well, today if you took 2,000 servers and 24 gigabytes is a fairly cost-effective amount of memory to put on each server, you get about 50 terabytes of storage at about $65 a gigabyte. Roll forward a few generations, assuming Moore's law stays with us a little while longer. You know, if you aren't doing it already, you should pray every night, for a few more generations of Moore's law before you hit the wall. In 5 to 10 years, it ought to be possible to build systems with a petabyte or more on the order of a few dollars a gigabyte. Now, if you've been tracking disk prices, you're gasping and saying, how could you possibly pay $65 a gigabyte for storage when disk is 50 to 100 times cheaper than that? And the answer is that RAM doesn't have to be cheaper than disk for everybody to start using it. It only has to be cheap enough. So for example, if you took all of Amazon's customer order data for a year, you could store that in about $100,000 to $200,000 worth of DRAM. Same for United Airlines flight reservation data. For those applications, $100,000 to $200,000 is in the noise in terms of the overall cost of them running their servers. So if DRAM provides some significant benefit, people will start to use it. So I would argue cost is no longer an obstacle. In fact, DRAM is cheap enough, I believe, that virtually all of the world's structured data, that is, things that are not media, images, photos, and songs, could be stored effectively in DRAM. All right, so now let me step back and talk about latency. And I'd like to address the issue, who needs 5 to 10 microsecond latency? Why is that important? And I think the easiest way to understand that is to compare applications of 10 or 12 years ago, before the web started taking over, to applications today in large-scale data centers. So before the web, that's the left side of the slide, the way you ran an application is that you compile it into a binary, you load the binary into memory, you also load all of the application's data into memory, and then you run the application. And the great thing about this is that the application has incredibly low latency access to its own data. You know, it's last level cache miss time, so that's 50 to 100 nanoseconds these days, which means you can run very intensive, very data-intensive algorithms like graph traversals and things that roam over data structures in very complex and interesting ways. The problem with this, of course, is that the overall throughput of this system is limited by the capacity of that one machine. So when the web came along and people started wanting to support not 10 users for one machine or 100 users for one machine, but 10,000 or 100,000 or 1 million or 10 million or 100 million, clearly you can't run applications that way. And so I assume I'm probably preaching to the choir on this, but over the last 10 years, what's emerged is this alternate style where we use thousands of machines running the application. And the most interesting thing about this, both the best and the worst thing about this, is that the application is now separated from its data. So you have the application running on a bunch of web front-end machines, and then you have, well, originally it would be database servers, now it's a collection of storage servers. And of course, in the stateless approach of the web, what happens is that when a request comes in over HTTP for a web page, the application servers will fetch the data that they need for that page from the storage servers. And once they've rendered the page, then they throw away all of the data they fetch. They're stateless. And so when the next request comes in, they start from scratch. So the result of that is that the application servers are constantly having to fetch data from the storage servers. And the unfortunate thing is that the latency now for an application to get at its own data has gone up by 4 or 5 orders of magnitude compared to what it was in the pre-web days. So if you think about that, if you ask the question, how many small reads can I do per second, say 100 byte or 1,000 byte reads, can I do per second with one machine over here and with 2,000 machines over here, 1,000 application servers and 1,000 storage servers? The answer is the one machine wins. Or depending on how you do it, you may be able to barely squeak ahead. But basically, we've got 1,000 times the number of resources, and yet we can only access the data at the same rate as with a single machine. So it's been very uneven scaling. We scaled CPU power, we scaled storage capacity, we didn't scale data access rate. And that's a huge problem for large-scale applications. I assume you're experiencing that here to some degree at LinkedIn. Well, we tend to use Facebook as our poster child for this. For example, at Facebook, when a web request arrives, they have to limit themselves to 100 to 150 internal data requests as part of generating that web page. If it takes longer than that, then the response times get too long and users get unhappy. And that's a huge hassle for them. It both restricts the kinds of applications they can provide, and it also results in huge complexity for the developers because they're constantly trying to find ways to get around this problem by, for example, having materialized views so you can get more data with one request, or trying to do things in parallel where the application allows that.
So, quick question. When you say internal requests, you mean off-box calls?
The question is, does internal requests mean off-box requests? So yes, it's requests over the data center network to storage servers to collect data that you need, presumably as part of generating a web page. So that's the problem. An interesting thing to consider in this world is MapReduce, which to me actually is very closely related to this problem. MapReduce has sort of solved this problem for a class of applications. What MapReduce does is it forces all the data accesses to be sequential. So I assume most people here are familiar with the basic paradigm, but the way it works is you start off with a whole bunch of very, very large files, and you stream those files through some number of servers in the first step. I drew 4 on the slide, but there'd typically be hundreds or maybe thousands of those. Each server reads one file sequentially, and then it generates an output file for each of a whole bunch of second stage servers. The second stage servers read all their files and generate an output file, which then gets combined to produce a result. One consequence of this approach is that since the data is accessed purely sequentially, you can go through a large amount of data very quickly. You don't care about the latency, but you only care about the bandwidth at which you can stream data through the various components. So MapReduce has largely gotten around this problem with high latency in web applications. But unfortunately, not all applications fit the MapReduce model. Actually, I've been pretty impressed at how many do. If you'd asked me 10 years ago, I wouldn't have guessed there'd be anywhere near as many things that you could squeeze into a MapReduce or Hadoop style of application. But the other problem with this is these are fundamentally offline applications. You typically can't do this to return a web page to somebody. You can do this if you're doing an overnight batch job to process all your logs from the day before or something like that. So both the best part and the worst part about MapReduce have to do with how it turns random accesses into sequential accesses. So what we'd like to do is to get the best of all worlds, to have the scalability that we get in the new web world, but to drive the latency of access down as close as possible as you can get to the old machine style. So for RAMCloud, our goal is 5 to 10 microseconds. There's nothing magical about that except that that's the lowest we think we can possibly do in the next few years. When we first started the project, I was arguing that we should try for 1 microsecond, and everybody laughed at me. In fact, they laughed in a fairly unkind way and continued laughing until eventually I decided they were probably right. And so we backed off to 5 microseconds. We think over the long term it might be possible to get down into the 2 microsecond range, but that would require some architectural innovations where the NIC gets integrated with the CPU much more closely. We've actually started trying to convince Intel to do this, but that's probably a 5 to 10 year kind of crusade to make that happen. So anyhow, how close can we get it? The faster the better. If we can do that, the tantalizing prospect is that a whole bunch of new applications will be possible that aren't possible today. And then people always say, well, what are those applications? Show me one. And then I start stuttering and stammering a little bit because the problem is that without a machine like this or a storage system like this, you couldn't really build those applications. They couldn't run on anything today. So it's a little hard to point to applications. There are a few. Facebook is clearly an application that would benefit from this. But as I've gone around and talked to people, I'm getting more and more ideas where people mention things that would happen. So very large-scale collaborative applications. I'm sure LinkedIn actually would be an example of this, but you can imagine many others. Massive multiplayer games is one example, but I'd like to think there are also others with more redeeming social value to them than just being able to kill more people in less time in your massive multiplayer game. Anything that involves very large-scale graph traversals, because those tend to be fundamentally random. You can't predict or stream that. You have to look at one node to know where you're going next. So then that includes a bunch of machine learning algorithms. So for example, Google's automatic translation system is traversing huge language models that are stored graphically when it does automatic translation for you and would benefit from something like this. Or any system that needs to manipulate very large amounts of information in very short periods of time to produce quick information for people. So my guess is there are a whole bunch of other things in logistics and anybody running a very large organization where you need to have very tight collaboration would have a need for it. If you hear of more applications, I'd love to hear about them, but I admit that there's a little bit of a build it and hope they will come flavor to the project. We sort of have to get the system out there and then see what happens. On the other hand, can you think of any example where somebody made some fundamental technology in computers 1,000 times faster and people said, yeah, nice, but I'm afraid there's just nothing we can do with that, sorry. So I don't think that's going to happen here either. OK, any questions about the motivation before I start talking about the system? All right. So a RAMCloud system will look something like this slide, where the RAMCloud system itself is a software package that runs on off-the-shelf hardware. So we're doing our development on Linux right now, using a large number of machines, at least 1,000 and hopefully 10,000 or more storage servers will be able to support at least that many. Each storage server has 2 components, a master and a backup. The master is the thing that manages data in DRAM and responds to client requests. I'll talk a little bit more about that in a bit. The backup is something that manages a disk or flash or some other secondary storage, and its job is to keep redundant copies of data from other masters. The backup on one machine typically doesn't store any of its master's data. It's only storing data for other masters. So there'll be hundreds or thousands or tens of thousands of these. Then there'll be a bunch of application servers. We're guessing that there are likely to be more application servers than storage servers. It seems like people tend to have 1 to 10 times as many application servers as storage servers. They access RAMCloud through a library package that will basically hide all of the distributed nature of the system. Applications can think about this as one logically centralized, very, very fast storage system. And then finally, there's one special machine called the coordinator, which manages the configuration of the cluster and also handles things like directing recoveries when machines fail, and so on. Individual requests would not normally pass through the coordinator. When an application first starts up, it would request configuration information from the coordinator telling it where various tables are located, and then would access the servers directly without going through the coordinator. If for some reason the configuration changes and some of that cached information turns out to be invalid, then the application goes back, actually the client library goes back and refreshes the cache from the coordinator. Yeah, question?
Is the coordinator a significant single point of failure?
Is the coordinator a significant single point of failure? We have to make sure that it's not. So we haven't actually implemented coordinator recovery yet, but that absolutely has to work. And there will be, our current plan is we'll have several backup coordinators waiting in the wings to take over, but only have one coordinator at a time. It's also, at some point, it will become a scalability bottleneck. We don't know what that point is yet, but one of the things we're trying to do in designing the system is to offload the coordinator as much as possible so we can push out the point where it becomes a scalability bottleneck. Yeah, but the coordinator has risks both in terms of scalability and reliability that we have to address. The data model for RAMCloud is currently very, very simple. It's a key value store with multiple tables. So you can have any number of tables. A table has any number of objects. Each object right now has a 64-bit unique identifier, a blob of data that RAMCloud does not understand at all. It can be up to a megabyte, and then a 64-bit version number associated with it. I'm not going to go through all the API functions, but they're the obvious key value store things. The only one worth mentioning is that there is a conditional write operation that takes a table and an object and a blob and a version number, and will only overwrite the object if its current version number at the time of the write matches the one specified there. And that's a hook that allows you to build higher level atomic primitives and transactions and things. So for example, you can read an object which returns its version number, update the object, and then make sure you only overwrite that object if no one else has modified it in the meantime. So it's the beginnings of doing transactional support. We think that this is way too bare bones of a data model for the long term. We'd like to try higher level things, and one of the interesting research questions is how high up can we raise the data model? Can we add things like indexes, multi-object transactions, graph support, and so on, before we start hitting scalability or performance bottlenecks? It seems to be the case. If we could do ACID, so do database SQL with ACID properties, probably everybody in the world would be delighted, but there seems to be a lot of evidence that you can't do that at scale. No one has been able to do it, and a lot of smart people are trying. So then the interesting question is, how high can you push the data model before you lose the scalability? And we don't know the answer to that yet, but we plan to. We'll push until something bad happens and then back off. So this is a really interesting project from a research standpoint, and there are a zillion really interesting and some pretty hard problems we have to solve in order to make it work. The two we've been working on over the last year are durability. How do we make this RAM data as safe as disk data? And then how do we achieve 5 to 10 microsecond round trip times for remote procedure calls? What I thought I would do today is focus mostly on the first one and talk a little bit about how we achieve that. If you ask me questions when we're done, I'm happy to address some of the others. And then there's a whole bunch of other issues that we will want to get to eventually, but we have done essentially nothing on so far in the project. So durability and availability. So the main thing is we have to make this data as reliable as disk, and we'd like to do it in a way that satisfies two attributes. First, we don't want it to affect the performance. So if we start getting disk-level performance out of RAMCloud, that would be a huge disappointment to us. We want performance that's limited only by DRAM and the speed of your network. And then the second thing is to do this in a way that minimizes the overall cost and energy usage of the system. So for example, one obvious alternative that we rejected would be to just make multiple copies in DRAM. Say, keep 3 copies of the data in the DRAMs of different servers in the cluster. The problem with that is that the DRAM is the primary thing that determines the cost of the system. And so if we replicate in DRAM, we've tripled the system cost, we've tripled the system's energy usage. And by the way, that still leaves us with problems when the power goes out, since obviously you lose all the DRAM. So we did not take that approach. Instead, the approach we took is to keep only 1 copy in DRAM. And then we keep backup copies on secondary storage, such as disk or flash. And there's a good news, bad news way of looking at it. The good news way of looking at it is that disk is so much cheaper than DRAM that keeping 3 copies on disk adds essentially nothing to the cost of the system. That's a few percent to the cost of the system. I guess the bad news way of looking at it is that DRAM is really expensive to start off with, so of course it can hide a lot of other costs. But this means that, again, the system cost is determined by DRAM. The durability doesn't cost anything. But it introduces some other issues, and I'll address both of these. The first one is, doesn't this mean we have to wait for a disk I/O during each write operation so that we know the data is safe when the write completes? And second, if we only have 1 copy in DRAM, what happens when we have a server crash? Then suddenly we don't have the data available. Do we have to read enormous amounts of data from disk and reconstruct information before we can continue operation after a crash? So let me take those one at a time. First, let me address the synchronous I/O issue. So what happens in RAMCloud when a write request arrives at a server, at a master, is that it makes a copy in its local memory. That's going to be the copy of record. And then it sends an operation log entry, the following object was written, to some number of backups. What the backups do is that they store that object information in memory and return immediately without writing anything to disk. Once the backups have all returned, then the master can return back to the client and say, we've got your data and we promise it's safe now. So the data isn't on disk yet. The way it gets to disk is that the backups collect a whole bunch of data. We use 8 megabyte things we call segments that we use for writing to disk. And then they write that all to disk in one big operation. And that way we can use the disk at its full bandwidth. We're not limited by disk seek times. We're limited only by the bandwidth of the disks. Once that's done, then the backups can throw away the copy in memory. So ultimately, the backup copies live only on disk. The backups keep information in memory only long enough to buffer up a bunch and write it to disk. Well, this leads naturally to a log-structured approach, at least on backups, where you're appending information to a buffer and then you write it out to disk. Turns out in RAMCloud, we use the log-structured approach pervasively. So the master's memory is also organized as a log, using a lot of the techniques from log-structured file systems. It means, for example, we have a cleaner that goes through and does garbage collection to reclaim space when objects get deleted, and so on. The log cleaning process is actually kind of similar to a generational garbage collection scheme, if you're familiar with the way that works. But actually, it's much more incremental and flexible than generational scavenging. We think that this actually is a really efficient way of organizing huge amounts of data in main memory. And there's a lot of evidence around that most of the existing memory allocation mechanisms fall down when they have large amounts of data in memory, when they get to have gigabyte data sets. We think that the logging approach may actually be more flexible and scalable than those. So the master's memory is essentially nothing but this in-memory log, and then in addition we add a hash table on so we can do fast lookups using a table ID and an object ID to find the object. And that's pretty much it for the masters. So this solves the problem of doing fast writes without waiting for disk. However, this still leads to a crash recovery problem. There's really 2 crash recovery problems now. The first one is that if a backup loses its power, then it potentially loses the information that it had saved in memory. And we can't afford for that to happen. The backups need to guarantee that the information they've buffered in memory is just as durable as the stuff they've written on their disk. So that means the backups need to have some kind of continuous power solution so that when the power goes off, they at least have enough time to flush all their buffered data out to disk. And there's a bunch of ways you can do that. One of the most interesting ones is that there are starting to appear memory modules that look and behave just like ordinary DRAM memory, except that they also have a little flash chip and a supercap capacitor on them with enough power so that if the main power goes off, this DIMM can all by itself flush its contents to the flash memory, and then it can be recovered from there when the system reboots. That's one possibility. Google uses per server battery backups in their data centers, so the machines all have enough power to last for a few minutes once the main power goes out, and they can flush volatile data. Or a data center-wide power solution is fine. Or even some enterprise disk controllers have battery backed up caches on the disk controller that you could use for this. So there's a bunch of options for that. All right, so at that point now, the data is safe on backups. We're still left with the problem with what happens when a server crashes. The problem is that when a server crashes, it doesn't even make sense to try and service IOs from disk. That's so slow, the system would be so incredibly slow that it would be essentially non-functional for people. And in fact, we have not saved any metadata around that allows you to do random access to disk. The only way to recover after a crash is we have to read in the entire log for that server, and we have to replay it so that we can reconstruct the hash table. While we're doing that, unfortunately, you can't service requests. So the way we've solved this problem in RAMCloud is to make the crash recovery really, really fast. And what I mean by really fast is 1 to 2 seconds to resume normal operation again. And the idea is that if we do that, then people won't even notice the difference, that that's fast enough that applications already suffer performance glitches in normal operation that can cause 1 to 2 second glitches. So there are probably some applications for which that's not fast enough, but in talking to people, it seems like for most of the applications we encounter, particularly web applications, it's fine. Because in the web, you often have delays of 1 to 2 seconds because of the network, anyhow. So then how do we do this? How do you recover if you have 64 gigabytes of memory on a master and you're going to recover that in 1 second? Well, there's no disk that can read 64 gigabytes of memory in a second. There's no network that can transmit 64 gigabytes of data in 1 second. How do you do it? The answer is you have to somehow use the scale of the system to do it in parallel. And so what I'll do next is walk you through a 3-step approach to how we do that. So the first approach, which is not a very good approach, doesn't use scale at all. In this one, this is sort of an obvious approach, which is you have each master pick 3 backups when it starts up, and it keeps a full copy of all of its data on each of those 3 backups. Then if the master crashes, what we do is we select somebody else, a new machine, to take over as that master. I'll call that the recovery master. And then what has to happen is that the data has to get read from the disks on the backups, transmitted over the network to the recovery master. It replays the log, reconstructs the hash table, and then resumes operation. Well, the problem with this, of course, is it takes way too long. The disks are going to be the first bottleneck. With 3 disks to read 64 gigabytes of data, you're talking around 3 or 4 minutes of time. So we're 2 orders of magnitude off our 1 to 2 seconds. So the solution is to use more disks and more backups working in parallel. And the way RAMCloud does that is that each master divides its log up into a whole bunch of modest-sized chunks. Again, we use the word segment to describe these. They're 8 megabytes each. And each segment gets backed up on a different set of backups. They're chosen more or less randomly with some extra smarts in there to make sure we even out balance it very uniformly across the backups. But the bottom line is that every master will have data on every single backup in the cluster. And so that way, when the master crashes, you can use all the machines in the cluster for recovery. So imagine using on the order of 1,000 backups. They can all in parallel be reading small chunks of the master's data. And then, so the second approach is massive parallelism of the backups. They all read the data in, transmit it over the network to the recovery master. Things go much faster. We don't have to wait very long for the disks. And if you do the math on that with 1,000 disks, we can now get all of the master's information back into memory in less than a second. So it's a good start. Unfortunately, we can get it into memory in a second, but the memory where we're getting it is the memories of 1,000 different backup machines, not the memory of the recovery master. We can't do that in a second because even assuming a 10 gigabit network, it takes about a minute to ship 64 gigabytes of data into this one machine. And even if we could do that, actually, with today's CPUs, just replaying the log and reconstructing the hash table, we couldn't do that in a second. It takes too long to do that. That would exceed the memory bandwidth of the machine. If you think about it, 64 gigabytes, our machines today typically don't have 64 gigabytes per second of memory bandwidth. So the next solution, is we have to have more recovery masters. We have to spread that work out. So if we could do that, say if we could take 100 machines, have each one of them recover 1/100th of the lost information, then if you apply the network speed, say 10 gigabits per second, now we can get the data into those machines in about half a second, a little bit more than half a second. So, and if we can somehow overlap this, the network transmission with the disk reading, we can get the whole thing done in about a second. And that is, in fact, how RAMCloud works. So when a machine crashes, what happens is that the coordinator slices and dices up the possessions of that master into a whole bunch of partitions. So in this particular case, I've shown a master with 4 partitions. The master is not partitioned in normal operation. But when it's time to recover, its data gets divided up, and the coordinator assigns different tablets, basically ranges of keys within tables, to a whole bunch of other machines. So each recovery master now only gets a little piece of the dead master's information. And then what happens is there's this massive parallel pipeline that gets exercised during recovery, where each backup reads the data from its disk, and then it divides that data up into pieces, one piece for each of the recovery masters. That data gets shipped over the network to that master, and then the master replays just the portions of the log for certain objects. As long as all the data for each object goes to the same master, we can replay that and figure out which is the most recent version and reconstruct a hash table. So that all happens in parallel, the reading from disk, transmitting over the network, replaying in the masters, reconstructing hash tables. And then presto, change-o, after about a second, all of the masters have read all their data, and the system can resume operation again. So that's the key idea. It's using massive parallelism. Is there a question?
Yeah, what's the key used for your application?
Pardon me?
What kind of key you're using for your application?
Yes, the question is, what kind of key are you using for the application? Well, the key, oh, for the partition. It's keys within tables. If you recall, the question is, what keys are used for partition? So if you recall, it's these 64-bit identifiers. It's a key value store, so applications pick the keys that they use for reading and writing objects. We basically take the key space for each table and divide it up into chunks where they're more or less equal in size. In fact, what actually happens is that the individual masters, during normal operation, they profile their tables to keep track of where the objects are distributed, both by bytes of data and by number of objects. And they produce something that we call a will. That is, a will or last testament. How should my possessions be divided in the event of my untimely demise? And they upload that will to the coordinator regularly. So when the master dies, it just goes and looks in the master's will. And from that, it can figure out how to divide up its tables and assign those to recovery masters. Yes?
Can these recovery masters be doing other useful work when they're not in recovery mode?
Good question. Can the recovery masters be doing other useful work when they're not in recovery mode? Yeah, the idea, in fact, is that these are just ordinary machines that actually are servicing their own information and tables. When a machine crashes, some number of the existing servers get asked to take on a little bit more work. We've got one more hungry mouth to feed. Can you handle a little bit more data? And so they just recover that data, and they incorporate it into their log, and they continue servicing it. So, of course, that means you have to run the system with a little bit of excess capacity so that you have the spare capacity when a machine crashes. But remember, if you're using 100 recovery masters, that's only a 1% chunk for each machine. So if you kept 10% spare capacity, that's enough to handle 10 crashes, for example. Another question, yeah.
What will happen when a crash master
It's the question, what will happen when a crash master comes back to life again? Yeah, so assuming we've recovered it, which we would normally expect to do, it will just re-enter the system as a blank machine ready for the cluster coordinator to manage, and the coordinator will gradually start assigning tablets to it. One of the other aspects of the system is that the system needs to be constantly reconfiguring itself, moving bits and pieces of table around as tables grow, as servers start running out of memory, or if tables are deleted. There'll need to be a configuration component that adjusts that. So when a new master comes in or a rebooted dead master returns, it just goes into the pool to be managed by the configuration manager. Yeah, question in back. Can we use the key value data model to do fast recovery? It's a partition based on keys. Yes, that's exactly what we do. We use those keys from the key value. Those are the things that we use to divide up. Yep. So based on particular key ranges, we'll get assigned to one recovery master. Another question. Yeah, the question is, what happens when the recovery master crashes? I think in handling crashes, the worst problems, I think, are always the second order problems. You solve the first order ones, and then there's the second order ones, like what if a second crash happens in the middle of recovery? So the project is young enough that we have not fully implemented that, so I can only kind of sketch the idea. But basically, if the recovery master crashes in the middle of recovery, we have to do two things. First, the coordinator has to assign that partition to some new recovery master so that we can recover from the first dead master. And then we have to also recover from the second dead master. So we have to start another whole recovery with another set of recovery masters for that. Yes?
If you're trying to request a piece of data that is in the process of being recovered, what does the coordinator do?
What happens if you're trying to request a piece of data that's in the process of being recovered? The answer is that the client gets deferred, gets delayed. It has to wait until the recovery is complete. And what will happen is that the client will go to the coordinator and say, where is this data? And the coordinator will say, sorry, we're recovering that, can't tell you right now. And then the client will back off and try again over time, and eventually the recovery will complete. The coordinator will then be able to say, it's alive again, here's where it is, and then the client goes off. But the goal is to make the recovery completely transparent. So applications running there should be no impact on the application of a server crash except for a delay, and the delay should all happen automatically inside the RAMCloud library. So the application developer does not have to worry about this at all. It should be completely transparent. Yes?
What happens in the case of intermittent network failures? And let's say a client requests some piece of data, and on the next request, the network dies. The coordinator also spots this, starts a recovery process, but the client, unaware of the recovery process being started, hits that same server again, the network is back up, and gets maybe a stale piece of data.
Yeah, so the question is, what happens in the event of intermittent network outages where you might tentatively decide a server is dead, but it's not really dead yet? Kind of reminds me of the old Monty Python skit, I'm not dead yet, where they're wheeling the bodies out in the famine. Actually, one of the worst things that can happen is an undead server. Because if we recover that to a different server and then the old server continues operation, now suddenly we have two copies of the data that can become inconsistent. So that's a bad thing. So we have to make sure, absolutely sure, that once we decide a server is dead, that it is truly dead. And we have various ways of doing that with pings and things in the system. That basically is the server, we use the simple explanation is a distributed lease mechanism, where if a server can't occasionally contact other servers to confirm that it still belongs on the cluster, it shoots itself in the head. So if we lose touch with the server and the coordinator tells everybody else on the cluster that it's dead, then when that server goes to basically renew its lease, somebody else will say, dude, I think you're dead. and then and then it will check back with the cluster coordinator and find out, yeah, it really is dead. But we have to make sure that when we say a machine is dead, it really is dead. Which actually reminds me of a joke, if I can pause for a second. You may have heard this one before, but there was a call to 9/11. And the operator picks up the phone, and there's a frantic man on the other side, and he says, I need help. I was out on a hunting trip with my buddy, and I shot him, and I think he's dead. And the operator says, well, let's be calm down. Let's first make sure he's dead. Long pause. There's a sound of gunfire in the background. Guy comes back to the phone and says, okay, what next? All right, other questions before I go on? Yeah.
So is there a reason every master picks its successors to will as opposed to be locked into directly?
Good question. Why do the masters create their own wills rather than having the coordinator somehow make that decision? The problem is the coordinator would then have to have information about what's stored on the masters, detailed information about which ranges within tables have which data. And so we're trying to minimize the amount of information the coordinator has to have and the amount of work it has to do. So instead, the masters compute it on their own, and then they just upload the will to the server, and all it has to do is store the will and then go back and consult it after the master crashes. But again, the goal is to absolutely minimize the amount of work that's done on the coordinator. A question way in back?
Doesn't the coordinator tell the application machine already that you need to talk to this master, write this data?
Doesn't the coordinator already have that information since it's telling the applications? It does, so it knows which tablets are stored on which master, but what it doesn't know is which of them have lots of data in them, which are small. How can I take those, say, for example, suppose a server just has one big table that it stores. How can I divide that table up into 10 equally sized pieces to assign to recovery masters during recovery? So it doesn't have information at that level of detail. Other question?
Yeah, so do you have some truncate on garbage clean your recovery log? Because you don't want your recovery log to go forever.
Do you have to garbage collect the recovery log? I think by that you're referring to this log here, which is stored on backups. Yeah, so the masters are responsible for that. The masters use a log cleaning mechanism to clean their own in-memory logs. And the way that works is that every once in a while, they find segments where most of the objects have been deleted. And they copy the live information to the head of the log, and then they can reclaim that old piece of memory. When they do that, then they go and they delete the corresponding segments from the backups. So the logs and the backups get cleaned up at the same time. One more question in the back, then I think I'll move on. For the master, the question is for the master to complete the write request, does it have to make sure that all the backups got the data? The answer is yes. It has to have received an acknowledgement that the data was stored in memory before it returns. It does not wait for the backups to push it to disk. Because again, the backups have made this promise that if I can put it in my memory, I have enough power to make sure it gets to disk after a power failure. Yes, the question is, does the master know how many backups it has? Yes, it does. And the next question is, what if one of the backups goes down? Good. Right, so that's the other aspect of recovery. What happens if a backup goes down? So backup recovery is a little bit simpler because it naturally distributes across the whole cluster. But if the backup goes down, most likely every single master in the cluster has data on the backup. That's sort of our goal, is to spread every master's data across the whole cluster. So when a backup goes down, the server notifies all of the masters, says we lost a backup. And then what the servers do is each server looks through its own table. It knows for each segment where all of the replicas of that segment were stored. And so for any replicas that were stored on the dead backup, it simply re-replicates that segment on a new backup. So, and that partitions very naturally. Every master probably only has a couple of segments on that backup. They can all do their work in parallel. They randomly assign the new replicas to other machines in the cluster, so there's not too much danger that 1,000 masters are going to be simultaneously trying to create a new replica on the same machine, and so on. In many ways, that's a simpler problem than recovering from masters. You don't have to replay log data to do any of that. You just have to make a new copy of the segment replica. Okay, let me move on. Let's see, did that. Yeah, so where are we status-wise? So this is a research project, but I actually don't like doing this typical university research where you build a research prototype that works just well enough to write a paper about it, then you give your paper and you throw the code away. Seems like a waste of effort to me. So we're actually, for RAMCloud, we're trying to build a production quality implementation. And I've been able to do this in previous university research projects, and we have a great bunch of students on the project, so I'm optimistic it's going to work for RAMCloud also. We've been coding a little more than a year now. And as I mentioned, the main focus has been on fast remote procedure call and the cluster recovery. We have the very simple data model implemented also with right now we have the cluster coordinator is sort of only a shell of a coordinator. That's probably the area that's least developed at this point. For our networking, we've built our RPC subsystems so that we can support a variety of different approaches to networking. We have an explicit transport layer that hides all the details of the networking. And we have a bunch of different implementations of transports. So we do TCP/IP through the kernel, which is easy but nowhere near fast enough for us. And the one we're using most is an implementation that uses Mellanox InfiniBand. So Mellanox has been nice enough to give us InfiniBand networking gear that has about 25 gigabits per second of raw bandwidth and can do round trips in a couple of microseconds. So using that, we are seeing read times in a small cluster of 5.2 microseconds. So this is not a data center with 100,000 nodes in it, so we're not at scale yet. But in our 60-node cluster, which is actually, that's a 2-level networking structure, we would need to go to 3 levels to get to 100,000 nodes. So at 2 levels of networking, we're getting about 5.2 microseconds. InfiniBand, it turns out, is very fast. It only adds 100 to 200 nanoseconds for each level of switching. So adding a 3rd level of switching would only add a couple of 100 nanoseconds onto those times. And we're currently seeing about 850,000 small reads per server. This is relatively untuned. Both of these times are relatively untuned, so we're hoping that we'll be able to make them better in the future. But these are already getting close to the range we hoped for the project, so that's encouraging. What I thought I'd do is give you just a couple of measurements of recovery so you can see how fast that really works. The first measurement indicates how much information can a single recovery master handle. So what we did is we created a machine, a server with data on it. We crashed that server. All of the server's data is in one partition, gets assigned to one recovery master, and we have, I forget, a large number of backups available. I can't remember if it's 30 or 60 backups available. So there's tons of disk bandwidth and tons of network bandwidth. The only limitation is the NIC on the master and the CPU in terms of how fast it can process the log. And then you can see how long recovery takes. So 1,000 milliseconds, that's our 1 second goal, as a function of how much data was in the crashed master. And the answer is the time varies depending on how big the objects are. If you have really small objects, it's the per object overheads that limit you. If you have really big objects, it ends up being the bandwidth of copying around all the data that limits you more than the per object time. And so we can actually recover more data a little bit faster if we have big objects, fewer hash table entries to make. But the answer is somewhere in the 400 to 800 megabytes can be handled by one master per second. So for the rest of the experiments, I'm going to use 600 megabytes, just the midpoint of that range. And the next experiment is, how scalable is this? The key thing is, can we really scale using a big cluster to recover a lot of data really fast? So the experiment we did is we start off with a really simple configuration, a crashed master with one 600 megabyte partition, one recovery master, and 6 backups. Turns out backups each have one disk at about 100 megabytes per second. So if we want to recover 600 megabytes in a second, we need roughly 6 disks per master. So do recovery that way. Then scale up, add a second partition, another recovery master, 6 more backups and disks, and so on, and keep doing that. And the goal is that as you scale this, the recovery time should stay constant. That is, as long as we keep scaling the cluster size, we should be able to scale the memory size in the same time for recovery. That's the hope. And this is the truth. So this is done with disks. Again, this is, over at this point, is one partition, one recovery master, 600 megabytes of total space. And then over here is 20 masters, 120 backups, 120 disks. We had to stop at just 20 recovery masters because at that point we'd used all of the 120 disks in our 60-node cluster. So we're out of resources. In this style of recovery, you're limited by the speed of the disks. In fact, you can see the blue line here is the slowest disk. If you look at each of the backups and how long it took it to read all of its data from its local disk, this is the time for the slowest backup. And you can see there's a little bit of a straggler effect. The average backup was taking the green line, but the slowest one was a little bit worse because the disks vary a little bit in performance. We actually trying to compensate for that in RAMCloud and try and adjust the layout of the segments to reflect if some disks are faster, we put more data on those disks and less on others, but we were not able to completely compensate for the variations in disk performance. So that's with disk. Then we got greedy and wanted to see, is there some way we can use all 60 of our recovery our nodes as recovery masters and go even faster? So we went out and bought a bunch of flash drives, and we put 2 flash drives on each backup machine instead of disks. And the flash drives have a bandwidth of about 250 megabytes per second. So in this scalability experiment, we used 2 flash drives per partition versus 6 disks per partition in the last one. Now, what you can see with 2 flash drives, it's going to take more than a second to get 600 megabytes. The partition size is the same. It takes more like 1.2 seconds to get 600 megabytes. But we still get pretty good scalability. Recovery time increased by about, I believe, about 15%, going from 1 master out to 60 masters. And by the time we get out here, we're recovering 35 gigabytes of data. So with 60 machines, we're getting about 35 gigabytes of data. That means we need up around 100 to 120 machines to recover a 64 gigabyte master. Yep. Yeah, the question, if I can abbreviate a little bit, is what about the issue of the switching fabric in the data center? particularly the higher levels of the data center, which in today's centers tend to be pretty seriously overcommitted, oversubscribed. We can have a 10x or 100x oversubscription. So that even if you have all these leaf machines trying to transmit at their 10 gigabits per second each, the top layers of the switching fabric can't accommodate all of that. So, so our assumption is for RAMCloud, and you can debate whether you believe this assumption or not, that within a few years, it's going to be cheap enough that data center networks will have full bisection bandwidth. So that the full fabric will be able to accommodate every machine transmitting and receiving at maximum speed. So we're not there yet, clearly. I think we're going to get there because if you look at what's happening with switching silicon, the chips from companies like Fulcrum and whatnot, where you can get a 24 or 48 port 10 gigabit switch on one chip that's a few $100s. And these are going to ride Moore's law over the next few years. They're going to get both faster and more ports per chip. And so we think it's going to be cost effective to build those kinds of networks. If you want to do RAMCloud style recovery on a big data center, you'll have to have a network like that to get the full speed. On our 60 node network here, by the way, we were using, I think it was 1.3 terabits of network bandwidth aggregated. That's spread across 60 nodes, but they're basically all running at 60 nodes, each running at about 20 gigabits of bandwidth. It's all running in parallel. Question?
Was there any write traffic on the backup nodes while you're doing the recovery?
I'm sorry, what's the question?
Was there any write traffic on the backup nodes while you were doing
The question is about the write traffic to backup nodes while we're doing recovery. That's actually the limiting issue for recovery, is that when the recovery master reads the data, it has to re-replicate that out as part of its log. And so it's writing the data 3 times. And that's actually where most of the network traffic during recovery comes from.
My question was not only about network bandwidth, but contention on the disks of the backup. Assume that those backup machines are constantly getting replicated write traffic from live masters, right? So there was some fight for the disk itself while you're doing the
Right, so the question is about contention for the disks of the backup. And I think your concern is that there's other normal write traffic going on at the same time that's interfering with that. Right, so we did our measurements on an idle cluster, which is sort of unfair in some sense. Although I would argue that in a real system, probably the most important thing is to recover fast. That I would argue recovery should get priority for all traffic. Because in a big application, if you have highly interconnected data sets, the odds are that everybody's going to hit the down server pretty quick. If you're assuming very large applications with a lot of interconnectivity. And so honestly, the most important thing is just to get things back in memory and get everybody running at full speed again. So if you want to keep servicing other operations, then to the degree that you're doing other things, if you want to have half your disk bandwidth available for doing other things, then what would have to happen is either your recovery will take twice as long, or you'd have to use twice as many machines. Now, we're only using 60 machines here for recovery. So if you have a cluster with say, a few thousand machines, we would not need to use those 1,000 machines at anywhere near their full disk bandwidth for recovery. We'd only be using 5 or 10% of the disk bandwidth of each machine for recovery. By the way, another corollary of this is that if we can recover one master with 60 other machines, that means if you have a few thousand machines, we think we could actually recover a dead rack in 1 to 2 seconds, 40 to 50 machines. Do them all by, again, using different recovery masters across the whole cluster. OK, so let me just wrap up. I mentioned at the beginning the goal is to have latency and scale. So we're getting pretty low latency now, pretty happy with that. We're not at the scales that people consider interesting for web applications yet, mostly because of our limited hardware resources at Stanford. We're hoping that at some point over the next year as the system matures, we will come across a commercial outfit that's interested in building a fast data center at larger scale, and we'd be delighted to work with them to try and run RAMCloud on that. We actually did some initial experiments at Facebook over the summer, for example. Anyhow, so we're not yet at large scale, but the results we're seeing so far are reasonably encouraging. If you look at those lines, they're pretty flat as we scale. By the way, in terms of where the project is, I should mention, we think we're about 6 to 12 months away from having a system that people might actually consider using for production use. I mean, it'll be a brave pioneers only kind of situation when we get there initially, but we think we're within less than a year of having a system that you might actually consider using for production. So to summarize the results, we're recovering memory sizes up to 35 gigabytes in just a couple of seconds. Scalability looks good so far. And the recovery mechanism allows us to make DRAM as durable and available as disk for basically the same cost as if you'd only had a volatile cache. So other people are building caches that aren't durable and spending as much money as we are. A lot of interesting research problems left to solve. But if we're successful over the next few years, I think the promise is first making it really easy for applications to use DRAM-based storage. So you can get all the full performance of DRAM. And then that, we hope, will lead to some really exciting applications that are bigger and do really wild and crazy things with very large data sets that aren't possible today. So thanks for your attention, and I'd be happy to take questions. Let's start with a question over here. Are we open sourcing this? Yes, this is totally open source. Actually, you can go to our Git repository now and download it. In fact, several people have already been able to get RAMCloud compiled and do some simple performance measurements. We even have a little benchmark suite that we have available. You can try it with your own data center with your own local network protocols and see what performance you get. If you Google RAMCloud, I think that will take you to our, we have a wiki. And then from the wiki, you should be able to find your way to the Git repository. But if you can't, Google me and send me email, and I'll give you some pointers. What language is it written in? C++. Yes.
So when you use this RAMCloud computation, where do you save your intermediate result? Is also in RAM or?
When you use RAMCloud for computation, where do you save your intermediate results? So I think RAMCloud would be a perfectly great way to save it. Depending on how intermediate it is, maybe you would just save it on a local machine while you're computing and then only put your final results in RAMCloud. But there's no reason why you couldn't save the data into RAMCloud also. So the goal is to be able to handle very high write bandwidth as well as read bandwidth. Is there a question here? The question is, would compression help given that we're limited by bandwidth in several places? Yeah, that's definitely an opportunity there. We have not explored it yet, but I think that would be an interesting thing to do. Yes.
Haven't talked much about how the data would be laid out in this cluster. Is that an interesting problem you guys would look at? Because obviously this is probably a general purpose storage system, so everybody's going to use it, right?
The question is about how data is laid out. Are you thinking in terms of how the applications would lay out their data, how they'd assign keys and things like that? Or are you thinking about how RAMCloud would lay the data out in memory?
How the coordinator would decide what to put where.
I see. How does the coordinator decide what to put where? Yeah, that's an interesting problem that we have only begun to talk about, and we haven't got anything interesting enough for me to tell you. But I think it will probably end up using the same mechanism we use for computing wills, where again we compute. We figure out how the data is distributed across a table, and then when one master server fills up, you can chop things up and distribute them. One of the interesting questions is to what degree will people depend on locality in RAMCloud? Will they want collections of things to be on the same server? And so we hope to make two promises about that. One is that we will try and keep tables, a whole table on the same server if we can. If the table's small enough to fit on one server, we'll try and keep that on the server. So you can know that all the data in one table is on the same server. And then second, if the table gets too large, we will try and keep adjacent key ranges on the same server. So as long as if you can allocate keys that keeps things that you want to access together on the same server, then you can do a multi-read operation that will get them all in one operation. All right, the question is about replication and backup. So replication, that should be handled by the RAMCloud system automatically. And by the way, you'll be able to select for each table, for example, how many copies of the data you want on that table. Backup is another interesting question or disaster recovery or cross data center replication is also, people ask about that. Right now, we're very focused on just getting things working in one data center. And so we haven't spent a lot of time thinking about how you do things cross data center. I'm sure that's going to come up as an issue, though. One nice thing about the logging approach is it makes it kind of easy to grab segments of the log and replicate those elsewhere if you want to. That's pretty easy to do relatively efficiently. And this is a problem we absolutely will need to look at, but it's one we have not gotten to yet. Other questions? Yes?
the log sequentially, how is it up to the application to decide whether they can tolerate dirty reads for the uncommitted data, or is it enforced by the RAMCloud?
The question is about consistency. Can applications get dirty reads? I assume what you mean by dirty read is
Read after write. So I wrote something. Can I rely that I will read my own copy only after it's made to disk or in the backup file? Or
so the question is read after write. If I write a piece of data and then I read it back again, is there a risk that I'll see the old copy of the data versus the new one? The answer is that with RAMCloud, we're promising very strong consistency. You will always see the last copy written, even if it hasn't been written to disk. That doesn't matter. Once it's committed into the memory of those backups, we've made our full durability and consistency guarantee. So even if those backups crash, we will guarantee that you'll see the most recently written copy of the data. Unless for some reason all three backups simultaneously crash. If they, for example, if that happens, that you exceed the replication level that we have for the system, then you could lose data. But assuming that our replication level holds out, that you've got enough replication, you would always see the most recent copy of each data item.
But you said that you don't replicate in main memory. And so my question was whether your client can see the data before it's made to the backup system.
Can the client somehow see the data before it's made it to the backup system?
Only in memory.
When it's only in memory. The client will only access the data through the master. The client will never talk to a backup to access data. And the master has a copy in its memory also. And if the master crashes, we'll recover that information using the mechanism I described for you. So we'd read.
This recovery works based on your log, which is on disk.
The comment is the recovery works based on the log on disk. That's correct.
So what happens in between when the write record is only in the memory log but hasn't made it to disk yet?
Right. So that's this. We'll go back to this slide. We write something to backup's memory, and then, for example, the whole data center power goes out. No data has been written to disk yet. The rule I mentioned about this is the backups have to guarantee that even in the event of a power failure, they can get the data to safe secondary storage before the power goes out. So basically, the backup has to guarantee that data in its memory is roughly as durable as data on disk. So if the backup machine explodes, we lose both. That's fine. But if the power goes out, the backup has to be able to get the data to disk before it breathes its last breath. Yes?
Can we use SSD instead of DRAM so that we can have a green data center?
Can you use SSD instead of DRAM so you could have a greener data center? You could certainly do that. The reason we chose DRAM is we wanted to push the performance envelope as far as we could. So if you use SSDs, you're going to have latencies in the 50 to 100 microsecond range, most likely. And we think we can do an order of magnitude better than that with DRAM. But if your application doesn't need DRAM speed, then I think that would be a fine thing to do. By the way, it turns out even with SSDs, you would need a lot of the techniques here in RAMCloud because you still have to handle node failures, for example. Yes? I'm sorry, what was the question? How utilized are the CPUs? A very good question. We don't know the answer yet. It's going to depend a lot on the access patterns and the applications. So right now, one server can sustain about 5 clients continuously hitting it. That is, it takes about a microsecond or 1.2 microseconds in the server to service the request. And it takes about 5 microseconds for each client. So roughly, we've got about 5 clients worth of bandwidth. So really, it depends totally on how data intensive the clients are, which is going to depend on the applications. So this is something we'll have to measure over time. And this leads to an interesting question about what's the right configuration for a server. How much memory can one server support before the CPU doesn't have enough bandwidth, for example, to satisfy all the requests for it? Well, again, we don't know the answers yet. And back. Let me see if I can restate the question. So the issue is a master crashes. We break up its possessions with a lot of small pieces and spread them across other nodes. Now, what if those nodes crash? do the pieces get split up more and more and more over time and just get finer and finer? So first of all, there's no reason why they need to get split up more and more, because once a partition has gotten small enough to be moved to a recovery master, then if that machine crashes, that same partition could stay intact, could be moved as a partition to some other machine. It doesn't, each individual partition would not need necessarily to be subdivided. The second thing is, though, but maybe even that's bad. If we really had a whole bunch of data that we wanted localized on one master, and we've now spread it across 100 masters, we've changed the locality properties for that application, and maybe that's not a good thing. And so that's where our configuration manager will come in. So once things have gotten up and running again, if we really wanted locality, it'll be up to the configuration manager to find these things and gradually start moving them back together again. So what that could mean is that for a short period of time after recovery, you're not getting optimal performance out of the system because we've lost some level of locality. But hopefully we'll be able to figure that out and then regenerate the locality. This is totally, I'm sort of making this up as I go because we haven't implemented any of this, but that's the idea that we hope to achieve. Yes?
What about the reverse? Let's say you have data that is very localized, but it's a hotspot, so you want to distribute that load among more cluster nodes. So that's not a recovery, it's not a failure, but spread it out.
Right. Right, that can happen in two ways. A master's memory can fill up, or you might discover there's such hot spots that you really want to split this up so that the master's machine can keep up with it. You know, 1 million requests per second is pretty good, but there will probably still be tables that will have more than that many requests per second. So again, we will need to detect this and change the configuration in response to this. Actually, the same thing we use for tablet profiling should work pretty well for this, because we're tracking all of the requests by tablet ranges, and so we should be able to start chopping up tables if we need to in order to distribute the load. Any other questions? Yes? How well does this play with internal caches? Are you referring to like the processor caches? Yeah, so we're not, RAMCloud is built on the assumption of very poor locality. That is, we're assuming that applications are making random, unpredictable accesses to this data set. Because if you had a lot of locality, you'd probably use a caching system instead of something like RAMCloud. And so we assume, for example, when a request comes into the server, that we're probably going to take a cache miss both for the hash table entry and for the log entry on disk. But we have a very tight time budget. Our goal is to service requests in less than a microsecond on the master. And so that means we have about 10 cache misses we get in that much time. So there's 2 we know of that we expect to get, but the rest of the code we think we should get pretty good locality on. But again, we're early enough on, we don't have a lot of good measurements, so I can't confirm that we're actually achieving that. I do know we're getting requests processed in about 1.2 microseconds right now, which is slower than I'd like. And I suspect it's probably because we're getting too many cache misses. Any other questions? All right, well, thanks very much. I'm happy to chat more about this afterwards if you have more questions.